Okay, year 12. I'm just going to go through some of the things that came up in the class yesterday. So I've sent you out this selection of questions, and we'll start with this one here. All right, so this question is really straightforward. All right, it's just about your understanding of the Arrhenius equation. Now, what was interesting was, I'm sure that you would all be able to do this question if you had access to your notes and sufficient time. But noticeably yesterday, a lot of people struggled with this because they didn't remember they couldn't remember the Arrhenius equation. They couldn't remember that here you've got the logarithmic form of the Arrhenius equation because you're talking about log k and 1 over t. So you need to know both of those forms, or you need to know how to get one from the other. And then, once you've got that, you need to remember that you can compare the logarithmic form of the Arrhenius equation to y equals mx plus c, where c is the y-intercept here. So in the logarithmic Arrhenius equation, whatever the constant is, that will be equal to this value here, and then you can use that to solve for the pre-exponential factor. All right, it was just interesting because I'm really confident you know how to do it and you understand it, but that at the time, having to recall those pieces of information was quite difficult for a lot of people. So it's like I said in the task, it's really important that you identify these things that you need to memorize. All right, so the very best students will just memorize what the y-intercept is, and they'll memorize what the gradient is. By which I mean, rather than memorize the equation, they'll know that the gradient for this is equal to minus EA over R, and so they'll just be able to work that out immediately. And the same for the y-intercept. All right. This question I think is quite straightforward, so you can use this information and this information to work out the concentration because you're asked for a concentration, and the half-life is 2 minutes and you've got 6 minutes, so it's basically 3 half-lives. Now, this question was where we sort of came across another significant problem, which was which things affect equilibrium constants. All right, so you can think about change in pressure, change in concentration, change in temperature, and the addition of a catalyst. Okay, now, in terms of the equilibrium constant, changing the pressure doesn't change it, changing the concentration doesn't change it, changing the temperature does, and adding a catalyst doesn't change it. Right? Now, if you think about the position of the equilibrium, changing the pressure will change that, changing the concentration will change that, changing the temperature will change that, and then the catalyst won't change that. All right, so when we think about these questions, you need to be comfortable thinking about them in terms of the equilibrium constant and in terms of the position of equilibrium. So it's kind of counterintuitive because you would think that if Kc doesn't change, the position of equilibrium doesn't change, but that's not true. All right, so you need to make sure that you're able to memorize these. So then when you get a question like this, you can immediately see, well, if I change it, so it's compressed at a constant temperature, so I'm not changing the temperature, but I am changing the pressure. So immediately you can discount A and B. All right, and then, so there's no change, but now it's, well, even though Kc isn't changing, is my position of equilibrium changing? Because if it is, then it will change the number of moles. I think that question's quite straightforward. You need to think about units, and you need to think about it being to the right-hand side and how big the value will be. It might be helpful for you if you wrote out what is the equilibrium constant for that equation, for that reaction. And that's just a straightforward rate order question. So you can see here that H2 is first order, NO is second order, and what am I doing? I'm going to halve this one, and I'm going to double this one. So if I halve H2, what does that do to the rate? And if I double NO, what does that do to the rate? And then if you combine those two effects, what's the overall effect on the rate? All right, moving on, that's easy. And then here, okay, so this is where people often make a very common error, right, which none of you want to do. So, calculating the amount of moles in H2 is straightforward. Okay, the key thing to realise is that you get 0.168 moles of C2H2, ethine. And if you look at the equation, you think, well, if I make 0.168 moles of this, how many moles of this will I make? Because at the start of the reaction, there's none of this. So at the start of the reaction, you only add CH4. Now, calculate the equilibrium constant. So Kc is C2H2, and then it's H2 to the power of 3 divided by CH4. Now, people that don't really know what they're doing, what they'll do is they'll take the values, they'll take this value, and the value they've worked out, and they'll put those values in here. Now, if you do that, yeah, you know, you've still got a basic understanding, but you don't really know what this equation is telling you, because you haven't remembered that these square brackets mean concentrations. And then you haven't realised that you've worked out a molar value in the previous part of the question. So in order to calculate this properly, you need to calculate concentrations, which you do with the volume. Okay, and then over here, again, you see now what we're doing is, this is a question about, this is Kc. The equilibrium amount of ethine, that's a question about the equilibrium position. And then we're now talking about rate as well. So we're combining these three. These two are quite similar. And then we're adding rate in as well. So this is going to tell us how much we're going to get, and this is going to tell us how fast we're going to get it. All right, so you need to think, does changing the temperature change this? No. Sorry, yes it does. Does changing the temperature change this? Yes it does. And you need to look at the fact that it is a, if I go back, it is an endothermic reaction. But then you need to think, what effect will increase in the temperature have on the rate? Now that's nothing to do with this specific reaction. You just know that increase in the temperature will increase the rate of any reaction. All right. So that's the kind of information you need to bring together. Here, the overall order of reaction is just the sum of the individual orders. It's a big number. Well, it's not a big number, it's 5, but don't be shy about putting down a number. You know, we've only talked about 1 or 2 or 0, but 5 is okay. Now, for this answer, suggest 2 reasons why it is unlikely that this reaction could take place in one step. Hopefully you're not just watching this video through. Hopefully you're doing the questions and then maybe stopping if you're not sure and watching this. If you're not doing that, then you should stop and do that. So once you've got to think about this, hopefully it's fairly obvious that you're not going to get 5 species colliding all at once. That's why it can't take place in one step. All right. Hopefully that's quite easy to understand. Now, where you would get the second mark, it's actually quite subtle, and you know, it discriminates well in terms of, if you get this question right, you're likely to get a very, very good mark in the exam. So what I'm going to do is, because this is quite a complicated example, I'm going to give you a more simple example. All right. Now you'll remember that for this situation, we can write down that the rate equals K A B. Rate equals K A B. Okay? And we know that the overall equation is going to be A plus B goes to D. All right, so the 2 conditions that we need to satisfy are that the 2 steps in the mechanism combine to make the overall reaction, and the rate equation matches the slow step. Okay? Now, the thing that you need to realise, and this is quite difficult, is that here it says, suggest 2 reasons why it is unlikely that this reaction would take place in one step. You need to realise that if this reaction only took place in one step, then the rate equation needs to match the overall equation, because that's the only step. All right, I'll say that again. If the reaction only takes place in one step, then the rate equation needs to match the overall equation. Okay, because the rate equation must match the slow step, and if there's only one step, that step must be the slow step. Okay, so if we look at our example, okay, if this reaction only took place in one step, this would be the equation of that step. This would be our slow rate determining step. And in order for that to be true, our rate equation would need to match the stoichiometric ratios in that equation. So if this was truly the only step, you would need to have rate equals ki to the minus 5, sorry, I minus to the power of 5, IO3 minus to the power of 1, and h plus to the power of 6. But you don't have that. So the second reason here would be that the rate equation, the stoichiometric ratios in the rate equation don't match the stoichiometric ratios in the overall equation. All right, I know that's complicated, so if that hasn't made a lot of sense, you'll need to watch that back a couple of times. Okay. Here again, all right. If you see this question in the exam, it's 2 free marks. Okay, really, it's basically just asking you to remember a straight line or a curved line, or does it go up or does it go down? But again, a few people yesterday, they understand it, they get it right eventually, but it's really, this should just be a reflex action. Once you see that question, it's like, well, I know that it's first order, it looks like this. It's the kind of thing you put on a flashcard. Okay. So these questions, you need a lot of practice on these. Most people are able to get this first one by comparing experiments 1 and 2. And then you'll get the third one. I think it's easiest to compare experiments 1 and 3. So look, here it's multiplying by 4. Here it's multiplying by 4. And here it's multiplying by 4. And you know the orders because you're given the orders in the rate equation. You don't need to do this question. Don't do that question. Then if we move on, that's straightforward as well. Now, this question. This is going back to what I was just talking about with, the individual steps add up to the overall equation. So here, you're now given the overall equation and 2 of 3 individual steps. So you need to come up with an equation here that when these 3 are added together, you get that one. Now, this is really important, okay, because we didn't talk a lot about this when we went through it the first time. Explain why this mechanism is consistent with the rate equation K equals H2NO squared. Well, I told you that the rate equation must match the slow step. Now, if it was to match the slow step, it would be rate equals K H2N2O2, but it's not, all right? And the reason is that if there is a fast step before the slow step, the rate equation matches the combination of those. Okay? So here you can see that if you were to add these 2 equations together, that would cancel with that, and you would end up with H2 plus 2NO goes to N2O plus H2O. And the rate equation does match that equation. All right. So that's just another piece of information you need to remember. And it makes sense because if you think about it, the concentration of N2O2 isn't affecting the rate because N2O2 is generated very quickly by the concentration of NO. So it's actually the concentration of NO that is affecting the rate. All right, because N2O2 is just this intermediate species. All right, so it doesn't make a lot of sense to have that in the rate equation. Okay, so that's another little thing you need to think about. Then, this one. Again, I think that's quite straightforward. It's, you know, again, people are going to make, I think actually here they're quite helpful where they tell you to work out the concentrations and then the value of Kc, so they've been quite nice there. And then I think that's all fairly straightforward. Here, actually, it says, state and explain in terms of Kc how the equilibrium yield of SO3 will be different from the yield in the first experiment. All right, now we did this in one of the lessons where we talked about, let's see, Kc is SO3 squared divided by SO2 squared O2. Now, what you need to do is they're saying, use Kc to explain how the yield of SO3 changes. All right, now what they've done is they've increased the amount of O2. But Kc has to stay the same. So if the value in the denominator increases, but Kc stays the same, what must happen to the value of SO3? Okay, and that's, it's, you know, so what they're looking for when they talk about explaining in terms of Kc, they are looking for quite a mathematical explanation of what's happening. And then that's straightforward. Here, now we're talking about Kp, so you need to work out not the concentration, you need to work out the partial pressure. So remember that Kp is going to be NH3, that's the pressure of NH3 squared divided by the pressure of N2, partial pressure of H2 cubed. And so, oh, sorry, you can't see that. And so you'll need to remember how to calculate partial pressures from mole fractions. And that's, you know, your typical rate equation question. Okay, now, what I've done with these questions is I've mixed together all different equilibrium and rate questions, okay, because those are two really, really key topics in chemistry. And I think people like to separate them, and they like to have them individually in their minds. You know, this is all about equilibrium, and this is all about rate. And equilibrium is all about how much you get, and rate is all about how fast you get it. But they're both very important, and something that affects one will affect the other, which is why it's important to have them mixed together so that you're constantly thinking about the effect of both of these things. The final thing that I'll say is, in these questions, little k, rate constant, and big K, equilibrium constant. Don't get those mixed up. Okay? So you can do that, and then if you could send your work to me, do the same thing, you know, with your phone, take a scan of each individual page. It will be helpful actually if you could, for this, scan each A5 page. You know, so scan each A5 page. Don't, you know, open it up and scan it like that because I won't be able to follow it. So scan each individual A5 page and then send that to me as a single PDF. If you do it against a dark background, and you can crop it, and it makes it really easy to mark. Now, finally, this cat. Okay, I recommend doing the exam questions before you do the cat, because this will warm you up for this. All right. because I think you can all do quite well on this as long as you're sort of in the zone. Now, there's only one question that you need to worry about. Well, you know, worry about them all, but this question here might throw you. All right, so this ester is hydrolyzed in the presence of water and a strong acid catalyst. A student obtained some data from which he deduced the amount of ethanoic acid in the reaction mixture over the first 300 minutes of this reaction. Describe how the student could obtain these data. Now, this question, it's a very, very common question. It comes up in the next CAT as well. So in CAT 19, you'll be asked a similar question here. All right, again, acid catalyzed hydrolysis of this ester. Outline how the student would then analyse the mixture to find the amount of moles of propanoic acid. Okay. What this question is asking you is, how can you determine the number of moles of acid, despite the fact that there is an acid catalyst, okay? Because what you'll need to do if you do this reaction is you'll need to extract some of the mixture. So you'll extract some of this mixture and you'll do a titration, okay, with sodium hydroxide, for example, and that will tell you how much acid has been produced. But the problem is that there is a strong acid catalyst. So you won't be measuring the number of moles of ethanoic acid produced, you'll be measuring the number of moles of ethanoic acid produced plus how much acid catalyst you had. So you'll remember that we did do an example of this. It was quite complicated. You can read about it, a similar example on page 296, or you can go back and you can watch the video. I'll try and find the video, I can't remember which one it is. Okay? But it is this idea that you need to make a special consideration if there's an acid catalyst. And it's a very, very common question, so you need to be able to do it. So what I want you to do is have a go at this one. I'll see how your answers look for this, and then when we do CAT 19, there's another chance to sort of really, really make sure you get it exactly right, all right? Because you can get a lot of marks once you've got it down, all right? Okay, that's everything. All right, send that in as well. And then obviously if you have any questions, please let me know.